Alright guys, welcome back to chemistry. This is once again Unit 3, Video 2 this time. So we talked a little bit about the periodic table. Now we're going to talk some about the history of the atom and its background and the scientists that have helped discover and started thinking about what the atom was and led us to where we are today. So there we go. Alright, so first things first, you need to know what is an atom. So it is the smallest amount of a substance that we can have and still retain features of that substance, okay? It is the basic unit of matter. Atoms make up everything, okay? All matter is made of atoms. And it is the fundamental unit of chemistry. The atom is chemistry. Okay, so let's give a round of applause for Mr. John Dalton here. We're going to talk about a few of the things that he did, what he proposed, which were true, which were not true. So, first things first, he said that all elements, right here, all elements are composed of very small particles called atoms, which are, key word right here, indivisible. Well, we came to find out, not we, not me, but other scientists came to find out this is not exactly true, okay? Because we can divide them into other things that we all know about, such as protons, neutrons, electrons, and there are many more, but we aren't going to go into those right now, all right? So, although this is what he believed, it was proven wrong, okay? So, the next one, he proposed that all atoms of the same element are identical. Once again, he was incorrect there, okay? Here's why. We have what's called isotopes, okay? And, for example, you might have a regular old carbon atom, and then you might have an isotope of carbon, which is known as carbon-14, okay? So it's the same element, but it is not exactly identical, all right? Third thing he proposed was that atoms of different elements are different. Well, of course. You have a copper, that's copper. You compare it to nitrogen or boron or any other element in the world, okay? Obviously, they're going to be different. Number 4, he proposed that atoms of different elements can combine with each other only in simple whole number ratios to form compounds. That's true, okay? So, in other words, we can take a sodium atom and a chlorine atom, okay? And we can add them together to make a compound, and it happens to be NaCl, or sodium chloride, your daily table salt, all right? And then number 5, he proposed that chemical reactions occur when atoms are separated or joined or arranged. However, atoms of one element are not changed into atoms of another element by a chemical reaction. Only by nuclear reactions may this happen. So he was correct there as well. Right. Our next guy here, J.J. Thompson. What did he discover exactly? Well, he discovered electrons are negatively charged. Okay, he figured out they were negatively charged. How did he do this? Okay, how did he figure out that electrons are negatively charged? Well, he used what we call the cathode ray experiment, the cathode ray tube, which is right here. Okay, this is your cathode ray tube that he used. All right, so he was able to figure out that these electrons are negatively charged. So what was his proposition, and was it true? He said the electrons are negatively charged. Was he correct? Yes, he was, okay. How did he figure this out? How did he know that this cathode ray tube showed that they were negative charges? Sorry about that. So let's look at this right here. You can see in this cathode ray tube here, this is a stream of electrons he's sending down it, okay? When it gets into this magnetic fields have a negative and a positive charge side here. When these electrons entered that field, as soon as they entered that field, he noticed they went opposite direction from where the negative charge right here was at, okay? On this plate here, he noticed that this negative charge was causing this stream of electrons to repel and go this direction. What does that mean? Well, it's kind of like the ends of a magnet. If you put the north and north together, they're going to repel. If you put the south and south together, they're going to repel, just like electrons. that a negative stream of electrons, as it went through there, it repelled the negative stream. Negative repels negative. So that is how he figured out the cathode ray experiment worked, okay? All right, so moving on. J.J. Thompson, he kept researching, I guess you could say, and came up with a second proposition. His second proposition was what we call the plum pudding model, all right? He said that the protons and electrons were mixed together like a fruit salad, like you see here in this picture, all right, or plum pudding. The larger pieces of the plum, quote unquote, were the protons swimming in a pudding of electrons, okay? Is this true? Why or why not? Why or why not? Okay, so today we know that there's not a little fancy green arrow here, so I'll just cross that one out. He was not correct when he thought that it was a plum pudding model, okay? Why not? Well, we know today that the positive charged protons are found in the center of the nucleus, and that your electrons, so here's your nucleus, and that your electrons in your outer levels out here are actually so teeny tiny, we know, that it wouldn't have worked with the electron stream that he sent through the cathode ray tube, because most of the space in an atom is empty space, okay? There's just this tiny little area that has this positive charge, okay? So he was able to, we were able to figure that plum pudding model was incorrect. All right, next was Ernest Rutherford. What was his proposition? What did he come up with? Well, he said that the atom is mostly space, and that all of the positive charge was located in a very small central nucleus. All right? So how did he test this proposition? How did he figure it out? Was he correct? All right? He was, in fact, correct, okay? And this is still what we know today about the positively charged, dense nucleus and the mostly empty space, okay? How did he figure this out? Well, he did what we call the gold foil experiment, right here, gold foil experiment, okay? So what he did was he shot this stream of particles, and there's a little clip I'm going to show you in just a minute that really explains it very well. He shot this stream of particles into some gold foil, okay? Most of these particles went straight on through, However, there were some that were deflected back in opposite directions, okay? There were a few out of them. So he could assume from this happening that because most of them went through, most of those were not hitting that positive nucleus, okay? But the ones that happened to hit the positive nucleus did bounce back, all right? But the other ones, because there's so much empty space in an atom, most of the particles, alpha particles, were able to actually go ahead and go on through without running into that little tiny bit of positively charged nucleus. So the positive alpha particles were hitting the positive small dense nucleus and getting deflected. Okay? So this is how we knew that Mr. J.J. Thompson previously was incorrect about his plum pudding model. All right? So here's a little explanation of your gold foil experiment.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
All right, so we can see from that video a little bit better explanation of what's going on in the gold foil experiment. All right, last guy that we're going to talk about is Niels Bohr here. He proposed what we call the planetary model, so to speak, okay? That electrons were in energy levels. The further an electron was from the nucleus, the higher its energy, all right? So So he called it the planetary model. Kind of like the different planets orbiting the sun. Okay, so he saw the electrons orbiting just like the planets do in the sun and all that. Okay, but hold on just a sec, guys. Sorry, I'm having technical difficulties. Okay, so this planetary model, well, we know it's a little bit different than what he had said, okay? We do know that there are energy levels like he proposed, but the planetary model isn't 100% true of how he said the electrons just sit there and orbit constantly, okay? Because we know today that they actually go from ground state to excited state back and forth, okay, from one level to another. So Niels Bohr did have the right idea that there are different energy levels. All right, guys, so that is the end of video 3. Once again, don't forget, we're here for your needs. Anybody needs tutoring, tutorials, here's your schedule. All right, thanks. Have a great day.